Now, alternating current is a flow of electrical charge that periodically reverses direction, like our AC generator we were talking about. If the source varies periodically, sinusoidally, most likely, the circuit is known as an alternating current circuit. So here I've got an example of what the voltage and current looks like in a DC circuit. It's constant here. In an alternating current circuit, we have these sinusoidal shapes for current in the voltage. Okay, and the equation, if you want to write the equation down for the shape that this voltage takes at any time, it's going to be the maximum voltage times sine of 2 pi times the frequency times time. Likewise, the current has a similar form. And F is the frequency of the signal in hertz or inverse seconds. So frequency is 1 over the period of oscillation. Let's see what happens when you place resistors, inductors, and capacitors inside alternating current circuits. So here's an example of what happens here. So we've got our alternating current and potential, and we see that the curves for the current and the potential line up with each other for the resistor. So the current and the voltage are in phase with each other. But when we look at the inductor and the capacitor, we see that the voltage and the current are offset from each other, and they're offset from each other by 90 degrees. Now over here is a plot of what happens when we have a alternating current power source, and we've got resistor, inductor, capacitor all in series. And so this green curve, that's the current in our circuit. This bottom potential curve is the total potential in our circuit. Okay. And these are the potentials across the resistor, the inductor, and the capacitor as a function of time. And so we see, let's just pick this time right here, this dotted line here, that at that time, the voltage across the resistor is at the maximum value, but the voltage across the inductor and the capacitor are 0. Now, if we go here a little bit of a time later, here we have that the voltage across the resistor just passed its maximum. The voltage across the inductor at that time is 0. The voltage across the capacitor has just on the underneath side of 0 here. And if we sum all of those up together, then we get the shape of the curve for the total voltage in our circuit, which will match the voltage coming from the AC power source at that time. Now, the important thing is that at any time t, if you sum up VR, VL, VC, the voltage across the resistor, the inductor, the capacitor, they will sum up to be the value coming from your power source. But if you take the maximum value of these at any one time and add up the maximum value that you can get on any of those elements and sum them up, that value will vastly exceed the potential that is being supplied, the maximum potential that's supplied by the power source. So if you want to find the maximum voltage being supplied by your power source, and all you know are the maximum voltages across your resistor, your inductor, and capacitor, then you can add them up in this special way right here. VR max squared plus the voltage across the inductor max minus the voltage across the capacitor max, all of that squared, and then take the square root of that. And so if you do that, then you should get back the value that is the maximum that's supplied by your power source. Okay, just by taking the maximum across any of your elements and adding them together will exceed what is being supplied by your power source. But if you take those maxima and you add them up in this special way, you will get back the maxima from your power source. If you were taking the measurements for all of these at the same time, and you found VR, VL, VC at some time, let's say t is equal to 1 second, and added them all up together, then you would also at that same time get the same amount as the voltage supplied by your power source. Okay, let's talk about a quantity called impedance that is also important in AC circuits. So the maximum current that can be achieved in an AC circuit is impeded by the circuit elements. The impedance has units of ohms, and the impedance of elements and their combinations is given by this chart here. So if you have a combination of a resistor and capacitor, this is the impedance for that circuit. If you have a combination of a resistor, inductor, capacitor, this is the impedance for that circuit. So the maximum current in an AC circuit is always given as the maximum potential, which is supplied by your AC source, divided by the impedance of your circuit. Okay, and so this would be the impedance of your circuit depending on the elements in it. And so these quantities that you see here, X sub C, X sub L, those are what we call the inductive reactance. And the inductive reactance for a capacitor is 1 over 2 pi times the frequency of the alternating current source times the capacitance of the capacitor. And the inductive reactance for an inductor is this X sub L, and that's equal to 2 times pi times the frequency of the alternating current source times the inductance of the inductor. So adding up these inductive reactances in certain ways with the resistance of resistors, you're able to get the total impedance of the circuit. It's this impedance that's important to what will help us figure out what is the maximum current you can get in any circuit that is an alternating current circuit. We have a series circuit with an alternating current source, a resistor, an inductor, and a capacitor. And this is very similar to a problem that you've been working through in your final lab experiment. So I'm not going to walk all the way through it by solving out all the numbers, but I'm just going to step through how you would solve this problem. So we want to find the impedance of this total circuit and then the maximum current that we can achieve within this circuit. So the impedance of this RLC circuit would be the square root of the resistance of our resistor plus the impedance of our inductor minus the impedance of our capacitor. Those two, that term, that subtraction term, all of that squared, and then we take the square root of that whole thing. And so remember that the impedance of an inductor is 2 pi times the frequency of our alternating current source times the inductance of the inductor. The impedance of our capacitor is 1 divided by 2 pi times the frequency of the alternating current source times the capacitance, okay? So you plug in those quantities depending on the frequency of your alternating current source, your inductance, your resistance, your capacitance, and you'll get the impedance, okay? This impedance affects the maximum current you can achieve in an alternating current source. So if we use Ohm's law and solve it for I, the maximum current at any time we can achieve is equal to the maximum voltage supplied by our alternating current source divided by the impedance of our circuit. And if you wanted to calculate the potential across any one of these elements individually, for the resistor, the maximum current, or sorry, the maximum potential you could get across it is just going to be the maximum current times the resistance of the resistor. For the inductor, the maximum potential across it at any during the time the current is flowing, the maximum current you'd be able to, or maximum potential you'd be able to achieve is equal to the maximum current times its impedance, the impedance of that inductor, and then the potential across our capacitor. The maximum potential across the capacitor would be the maximum current times the impedance of the capacitor. Okay, so if you find the maximum potentials across that you can achieve across any of those elements, and you sum them up, you would find that they would exceed the maximum potential that is being supplied by our alternating current source. And that's because in an alternating current RLC circuit, the curve that you can plot for the potential across any of those elements are offset from each other. So while one of them is achieving their maximum value, the other two might not be achieving their maximum value. And so if you sum all the potentials up at any time across all of the elements, you will get back the potential of your power source. But if you take the maximum value that any of these achieve across them for the potential and sum those up, that number will vastly exceed what the maximum potential is coming from your power source, from your alternating current source.